Welcome students, Module 3 Covalent Bond. The instructor of this video is Mrs. P. Arunajyoti, Assistant Professor in Chemistry, St. Joseph's College for Women. We can watch the different types of hybridizations. Hybridization is a concept that explains the formation of different types of bonds and shapes of molecules by mixing atomic orbitals of different energies and shapes. There are different types of hybridization based on the number and type of orbitals involved in the mixing process. Here are some examples of hybridization with the diagrams. Based on the types of orbitals involved in the mixing, the hybridization can be classified as sp, sp2, sp3, sp3d, sp3d2 and sp3d3. You just don't bother about the sp3d3. We have to learn the remaining hybridizations like sp, sp2, sp3, sp3d, sp3d2. Let us now discuss the various types of hybridization along with the examples. The first type of hybridization is sp hybridization. What is sp hybridization? One s atomic orbital and one p atomic orbital gets hybridized to form 1 plus 1 2 sp hybrid orbitals is known as sp hybridization. In sp hybridization, there is an involvement of s character is 50% and p character is 50%. The applied example for sp hybridization is beryllium dichloride molecule. The formula for beryllium dichloride is BeCl2, in which the central atom occupied with the beryllium atom. Around the beryllium atom, you can see the two chlorine atoms, which makes an angle 180 degrees. The shape of the beryllium dichloride is linear shape. Coming to the beryllium atomic number, you know that is 4. Its electronic configuration is 1s2, 2s2, 2p0. Ground state electronic configuration of beryllium atom has 2 electrons at 2s level, no electrons at a 2px, 2py, 2pz level. Coming to the excited state electronic configuration of beryllium atom, there is only one unpaired electron at a 2s level, one more unpaired electron at a 2px level. These two unpaired electrons of the beryllium overlaps with the two unhybridized p orbitals of the two chlorine atoms to form a linear shape. What do you mean by excitation? Excitation means the transfer of electron takes place from the lower energy levels to the higher energy levels. Means you should jump the electron from lower energy levels to the higher energy level. Initially 2s has 2 electrons. After excitation it has only 1 electron due to the jumping of one electron from 2s level to the 2p level. These two gets hybridized to form sp hybridization. Beryllium can provide two sp hybrid orbitals. They should overlap with the unhybridized p orbitals of the two chlorine atoms to form two sigma bonds. You know that chlorine atomic number is 17. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. It has one unpaired electron at the pz atomic orbital. That unhybridized pz atomic orbital of each chlorine overlaps with the sp hybrid orbitals of the beryllium atom, forms two sigma bonds. This is the first sigma bond between the beryllium and chlorine atom. Second sigma bond between the beryllium and the chlorine atom. Here the bond angle is 180 degrees and the shape is linear shape. It is about sp hybridization. The next type of hybridization is sp2 hybridization. In this type of hybridization, one s atomic orbital and two p atomic orbitals gets hybridized to form 2 plus 1 3 hybrid orbitals is known as sp2 hybridization. There is an involvement of p character as 66.66 percentage and the s character is 33.33 percentage in sp2 hybridization. The best example we can apply for sp2 hybridization is boron trichloride molecule. Boron trichloride molecule has the formula BCl3. In BCl3, the central atom is the boron atom surrounded by 3 chlorine atoms, which makes an angle 120 degrees. The shape of the BCl3 is trigonal planar geometry or planar triangular. The atomic number of boron, we know that that is 5. And its electronic configuration is 1s2, 2s2, 2px1, 2py0, 2pz0. Coming to the ground state electronic configuration of boron atom, its outermost level has 2 electrons at 2s level, only 1 electron at 2px level. In excited state, what you have to do here, you should do the excitation process, means you should jump 1 electron from lower energy level, that is 2s level, to the next level, 2px level. Now it has only 1 electron at 2s level and 2 electrons at 2px level and 2py level. Okay, then what is the excited electronic configuration of the boron atom? Only 1 electron at 2s level, 2 electrons at 2px level and 2py level. All these gets hybridized to form 2 plus 1 3 hybrid orbitals. Boron can prefer to provide 3 hybrid orbitals. These 3 sp2 hybrid orbitals from the boron atom overlaps with the unhybridized p orbitals of all the 3 chlorine atoms, which makes 3 sigma bonds. You know that chlorine atom atomic number is 17 and its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Coming to the outermost electronic configuration, it has 3p5. Each chlorine attains 3p5 at its outermost electronic configuration. 3p5 means 1 electron is left over in the pz orbital, that is unhybridized pz orbital. All the unhybridized pz orbitals of the 3 chlorine atoms gets intermixed with the 3 sp2 hybrid orbitals of the boron atom, which makes 3 sigma bonds. First sigma bond, second sigma bond, third sigma bond. Okay, therefore, the obtained shape from the boron trichloride is trigonal planar shape. It is about the sp2 hybridization. The next type of classification is sp3 hybridization. Here, the mixing of 1 2s atomic orbital and 3p atomic orbitals to produce 4 hybrid orbitals with the comparable properties is referred to as sp3 hybridization. An atom needs 3p atomic orbitals and 1 s atomic orbitals in order to undergo sp3 hybridization. The best example for sp3 hybridization is methane molecule. The formula for methane molecule is CH4, in which the central atom is occupied with the carbon atom surrounded by 4 hydrogen atoms, which makes the shape is tetrahedral geometry. The carbon atom atomic number is 6 and its electronic configuration is 1s2, 2s2, 2px1, 2py1, 2pz0. Its ground state electronic configuration has 2 electrons in 2s level, single electrons in 2px and 2py levels. Coming to the excited state electronic configuration of carbon atom, now it has only 1 electron in 2s level, 3 electrons in 2px level, 2py level and 2pz level. Here you must do the excitation. There is a migration of electron from lower energy level, that is s level, to the next level, 2pz level. All these 4 electrons, unpaired electrons from the carbon atom, gets intermixed to form sp3 hybrid orbitals. Carbon can prefer to provide 4 sp3 hybrid orbitals. All these 4 sp3 hybrid orbitals tend to overlap with the s orbitals of the 4 hydrogen atoms, which makes an angle 109.5 degrees. The obtained shape from the methane molecule is tetrahedral shape. It is about sp3 hybridization. The next kind of hybridization is sp3d hybridization. sp3d hybridization involves the mixing of 1 s atomic orbital, 3p atomic orbitals and 1d atomic orbital to form 3 plus 1 plus 1, 5 sp3d hybridized orbitals of equal energy. They have trigonal bipyramidal geometry. What is the difference between previous hybridizations and sp3d hybridization is there is an involvement of d atomic orbital along with the s and p atomic orbitals in sp3d hybridization. The applied example for sp3d hybridization is PCl5 molecule. PCl5 is known as phosphorus pentachloride. Phosphorus occupied at the central position. Around the phosphorus, you can see 5 chlorine atoms, which makes an angle. Two types of bond angles, those are 120 degrees and 90 degrees. The shape of the phosphorus pentachloride is trigonal bipyramidal shape. Coming to the phosphorus atomic number, you know that is 15. Its electronic configuration 1s2, 2s2, 2p6, 3s2, 3p3. Ground state electronic configuration of phosphorus atom has 3 unpaired electrons at 3px, 3py, 3pz levels. No electrons at a 3d level. In excited state electronic configuration, it has 1 electron in 3s level, 3 unpaired electrons at 3px, 3py, 3pz levels, 1 more electron at a 3d level. Here there is a transfer of electron takes place from lower energy level, that is 3s level, to the 3d level. All these 5 unpaired electrons from the phosphorus atoms forms 5 sigma bonds with a 5 unhybridized p orbitals of the 5 chlorine atoms. The obtaining angles from the PCl5 molecule are 120 degrees and 90 degrees. The shape attaining from the PCl5 molecule is trigonal bipyramidal geometry. The mixture of spd orbitals forms, we know that is trigonal bipyramidal symmetry. Three hybrid orbitals lies in a horizontal plane inclined at an angle of 120 degrees to each other, known as equatorial bonds. These bonds are equatorial bonds. The remaining two orbitals lies in the vertical plane at a 90 degrees plane of equatorial orbitals, known as axial orbitals. The best example for sp3d hybridization is what? PCl5 molecule. It is the information regarding sp3d hybridization. The last type is sp3d2 hybridization. Here the intermixing of one s orbital, 3p orbitals and 2d orbitals of almost having a same energy by giving 6 identical and degenerate hybrid orbitals is called sp3d2 hybridization. These 6 sp3d2 hybrid orbitals are arranged in octahedral symmetry by making 90 degrees angles to each other. This arrangement can be visualized as 4 orbitals arranged in a square planar, and the remaining two, this is the structure of square planar. The remaining two orbitals are oriented above and below this plane perpendicularly. The given example for sp3d2 hybridization is SF6. Here the central atom is the sulfur. The surrounding atoms are 6 fluorine atoms. In SF6, one electron each from 3s and 3p orbitals is promoted to the 3d orbitals. The 6 orbitals gets hybridized to form 6 sp3d2 hybrid orbitals. See, 1 electron in 3s level, 3 electrons in 3px, 3py, 3pz orbitals, 2 electrons in 3d orbitals. Each of these sp3d2 hybrid orbitals overlaps with the 2p orbitals of 6 fluorine atoms to form 6 sulfur fluorine bonds. First sulfur fluorine bond, second bond, third bond, fourth bond, fifth bond, sixth bond. We'll get total 6 sigma bonds. Okay, here you can see the double excitation. There is an availability of empty d orbitals makes the electrons of s and p orbitals excited to the empty orbitals, which results the octahedral geometry in SF6 molecule. It is about sp3d2 hybridization. Coordinate covalent bond. Coordinate covalent bond is a type of alternate covalent bond.
that is formed by the sharing of an electron pair from a single atom. How could you form the covalent bond? It is a mutual sharing of electron pairs between any two atoms in a molecule is known as a covalent bond. Such type of mutual sharing cannot be seen in a coordinate covalent bond. Both shared electrons are donated by the same atom is also known as dative bond or a dipolar bond. Coordinate covalent bonds are usually formed in the reaction that involves two nonmetals. You could observe the coordinate covalent bond between any two nonmetals such as hydrogen atom or during the bond formation between metal ions and ligands. You can see the coordinate covalent bond in a coordination chemistry in which the coordination compounds made up of metal ions at the center surrounded by the ligands. The ligands have the capability to release or to donate its electrons towards the empty orbitals of the metal ions such that we will make the coordinate covalent bonds between metal ions and ligands in coordination chemistry. Coordinate characteristics of a covalent bond. In this type of bonding, the atom that shares an electron pair from itself is termed as the donor. Which atom or a group or a species have the ability to produce or release electron pair towards the neighboring agent is known as donor. The other atom which accepts the shared pair of electrons is known as a receptor or acceptor. The agent or a atom or a group or a species have the ability or a capability to receive the electrons from the neighboring agent is known as a receptor or acceptor. This bond can be represented with an arrow, single-headed arrow. It should be pointed towards the acceptor from the donor atom. All the coordinate covalent bonds can be represented by an arrow, single-head arrow. Below we have given a simple diagram of the coordinate bond. The bond is shown by an arrow which points in the direction where an atom is donating the lone pair to the atom that is receiving it. Example 1. Nitrogen atom in ammonia donates its electron pair to the empty orbital of the H plus ion. The nitrogen atom has a lone pair of electrons in its outermost electronic configuration. So due to the presence of lone pair of electron on the nitrogen atom, it has the ability to produce the electron pair towards the vacant orbitals of the hydrogen atom in a hydrochloric acid. Thus, nitrogen considered as a donor and H plus is considered as an acceptor. And we can see the formation of the coordinate covalent bond in the example 1. Example 2. Something similar happens. A hydrogen ion, H plus ion, is transferred from the chlorine to one of the lone pairs on the oxygen atom. Here, the coordinate covalent bond is formed between the oxygen atom of water molecule and hydrogen atom of the hydrochloric acid. Oxygen actually carrying two lone pairs of electrons on its outermost electronic configuration. Out of two lone pairs of electrons, one lone pair donated to the empty orbital of hydrogen atom of a hydrochloric acid makes the coordinate covalent bond. In this example, oxygen atom of water molecule acts as a donor and the hydrogen atom of hydrochloric acid is acting as a acceptor to form a hydronium ion. The H3 plus O plus ion is variously called hydroxonium ion, hydronium ion or oxonium ion. In an introductory chemistry course, whenever you have talked about hydrogen ions, for example in acids, you have actually been talking about the hydroxonium ion. H2O reacts with the HCl to form H3O plus plus Cl minus ion. This H3O plus ions generally called hydroxonium ions. A raw hydrogen ion is simply a proton and is far too reactive to exist on its own in a test tube. You just neglect this sentence. It is about the coordinate covalent bond formed between the H2O and HCl molecule. All these are the examples for coordinate covalent bond. All the images in this video have been taken from Google Chrome. Thank you.